Hey, welcome to another episode of Transparent Physics. We're starting off in a new location today. You can see I'm in an Excel spreadsheet. And this is an Excel spreadsheet of my own design. What I am doing here is simulating pennies being flipped. Now, flipping pennies is a classic activity that we can use to simulate the idea of a half-life. And a half-life is something we'll talk about in more detail later in the video. We introduced in an earlier part of the lesson the idea that some nuclei are unstable and they will decay over time. So what we do here to sort of simulate that is to have pennies. And let's say that if your penny flips and is heads up, it does not decay. It is undecayed. If your penny flips and it's tails, it decays. When a penny decays, we take it out of the mix so that we don't worry about it anymore, and we only flip the undecayed pennies again, quote unquote. I used air quotes. I don't know why I did that because you can't see that, but the idea is that pennies that come up heads go back in the cup, get shaken again and tossed out, and then we check. So for example, for penny number one, again, everybody starts off undecayed. We all go in the cup to start. So after the first flip, it came up heads, came up heads, came up heads, and then it got tails. So the way this is set up is if I mess around with it, it will randomize. So that we'll just go with this data then. So new set of data. First penny comes out, gets tails right away. Second penny comes out, gets tails right away. Third penny comes out, gets heads, gets flipped again, gets tails. Fourth penny, heads, heads, tails. And that's the idea. So it goes across, 10 pennies represented overall. And as you sort of saw a sneak preview of it, every time I sort of jiggle the sheet a little bit, it will create this new randomly every time. And what we can see is like this one, a lot of them bailed out pretty quickly. We were only, after the first flip, we only had 3 pennies left, and this all ended kind of rapidly. So you can see there's a lot of variation when we do this. Every time things just end up working out their own way. So in this case, this guy lasted pretty long. He lasted 5 flips. So that means you got heads, 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 and tails. That's unusual. We don't expect to see that, but it can happen if we watch long enough. That guy actually went even a little further. So hours of fun simulating 10 pennies being flipped. But you might be asking yourself, 10 pennies being flipped? I mean, can you do better than that? Transparent physics. And the answer is yes, I can do better than that. Now, I really only formatted the first couple ones because that's the ones I knew we would be looking at. Another one where they almost all drop out. Oh, look at this guy. So we have this guy who just keeps going, man. Heads, 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 tails. So statistically, again, I'm sure I could work out the numbers as far as how often that would occur, but that is a penny that lasted a very long time under trying circumstances. So we're going to leave it at that. But in any case, if I scroll over, what we can see is this process repeats itself 100 times, 200 times, etc. And it actually goes for 10,000 iterations. So if I scroll over and keep going, and the column that is 10,000 ends up being nut. So pretty nutty to do this much data, but that's the way it goes. So I've got a 10,000 simulated pennies, all flipping, all independent of each other. When you get heads, it goes back in the jar and gets flipped again. When you get tails, it gets removed and we do not flip it again. This stuff here is just some formatting I use to make my graphs look prettier. And let's take a look here. Now, this is a graphical representation of the columns I was just showing you. Makes it a little easier to see what's going on. So for instance, if I, just for the record, if I take a look at my first 10 here, without randomizing it hopefully. All right, so in this first set of 10, you can see that we have 1, 2, 3, 4 pennies that survived the first flip. And then after this first flip, from the second flip, it's just 1 penny the whole rest of the time. So remembering that data, hopefully I can do this without resetting everything. Let's take a look here. And the 10 penny graph shows us, little sneak preview there. Let's just go with the 10 pennies. Oh, that's right. We didn't go over far enough. Pew. Back to 10 pennies. There it is. So I'm saying 10 starting atoms, if you will, where the pennies are represented or represent atoms. And you can look and see that this data works out exactly the way we saw in the columns. After one flip, we have 4 pennies that are left as heads. Then from there on out, we have that super penny that just goes the long time there before it eventually drops out. So I just stopped graphing the data in this one. But I think he drops out right after that one. That's just a coincidence, but still, good way to go, Penny. Now, I can continue the simulation here, and again, every time I just change the value in a cell, you can see the bars flip. Now, you might be asking yourself, what do these lines represent? The expectation here is after 10 flips, or sorry, after 10 pennies, after one flip, we would expect to see, on average, 5 pennies that come up heads. The green line would drop down to 5. So 5 pennies as tails, 5 pennies as heads. The gray line here represents pennies that have decayed, quote unquote, to tails. In this case, you can see this particular sample, the numbers don't really support that average. We take 10 pennies and 8 of them still ends up as heads. And then we take 8 pennies and flip them and 6 of them are still heads. So it is lasting, in this case, longer than it seems like it should have. But again, that's just a random distribution. I could do it again and I might end up below it. Actually, this one worked out perfectly as far as that one goes. So we go from 10 to 5. Now technically, when you have 5 pennies, you should end up somewhere between 2 and 3 on average. Here we only lost 1 penny. That's a little unusual. And so that's what these lines represent. The first line represents our expected drop after one flip. The blue line represents our expected drop after 2 flips. The orangey-ish line, burnt orange, is the number that we would expect after 3 flips. And the red line is the number we would expect after 4 flips. Technically, I could keep going further, but it gets kind of crowded at the bottom. And you can also see that at the bottom each column, I have printed the number that represents the remaining heads, if you will, the number of pennies that are still heads. So I can keep flipping it, and the values change. Again, sometimes, like in this case, it bottoms out really quick, and you can see definitely at other times it keeps going for quite a long time. Generally speaking, you can see it definitely tends to drop a lot and then sort of level out, but there's really not enough data here to really draw a trend. Every penny is a random flip. Every penny is a 50% chance of getting one or the other. But with 10 pennies to start, 10 atoms to start, the randomness can sometimes overwhelm the trend, and we can end up with these sets of data that don't necessarily match what we would think to see. Despite the fact every penny is 50%. It's random. A small data set does not always show us the trend that we think we're going to see. So what we can do is we can instead take a look at a larger set. So here, this is 100 pennies. So I'm taking the first 100 sets of data. So already you can see that the trend is cleaner. This is the same set of data that I was looking at to the left, but there are more pennies. There's 90 more pennies set in here. So the first 10 pennies are in there, plus 90 more. In this case, 100 drops pretty cleanly almost to 50. Almost 50 drops pretty cleanly almost to 25. Almost 25 drops pretty cleanly almost to 12. And almost 12 drops pretty cleanly to 6-ish, 7-ish. All right. And again, this one actually works out pretty much exactly like we would expect to see, with half of the sample disappearing each time. Now, this one just happened to be a pretty good one. Even with 100 pennies, the values don't always show us what we think we're going to. That one, the pennies dropped out a little slower at the start. That one, the pennies dropped out a little faster at the start. You can see the trend is cleaner. It's definitely more predictable than it was for the last set, and they are tending to hedge closer to these lines, but it's not perfect. And that's 100 atoms. You probably know where this is going. It's going to 1,000 atoms next. That's where it's going. So I'm just expanding the set of the data here with 1,000 atoms. Again, we don't need to belabor the point too much there, but you can see every time I rearrange it, we are getting closer to those lines that we expect to see. It's not always perfect, but it's not bad. So 1,000 drops to around 500. Around 500 drops to around 250. Around 250 drops to around 125. Then it drops a little faster than we would think it would, but it's not bad. And if we compare these lines to the bar lines that we saw for the 10 penny graph, these are much more consistent. They're not perfect, but they are much more consistent. Because even though every penny flip is random, this is, again, I still think it's kind of neat, the idea that you have 1,000 totally random events, but it ends up working out that around half of it, 1,000 completely random events, but we end up usually working right around to being pretty close to 500 every time. The larger your sample set is, the more cleanly you'll see the trend in the randomness. And then we'll do our Zambelli fireworks finale. That's a bit more of a local Pittsburgh reference there, but the idea is that here we have our full 10,000 penny set, and when I run it, again, even here it is not perfect, but you can see the variation is very small between each run. It's not there's any less randomness in every individual flip, but there's just so many pennies in the mix that overwhelmingly the trend is going to show what we expect to see for the pennies. 10,000 random chance events, and look at this right here. After one flip, almost perfectly half of them decay. Around 5,000, after a second flip, again, almost perfectly half of them decay. Not half from the start, but half of what we had after the first flip. Half of what we had after the second flip drops here, half of what we had after the third flip, etc. So you can see, and again, if I had continued these lines down, we would see them matching those trends cleanly. This idea of starting with something and losing half of it, and then losing half of what you had left, and then half of that, and half of that, this ties in very closely to the idea of half-life. And I like this kind of activity because we're going to talk a little bit more about the nuclei in a second. The nuclei decay. Every nucleus is a random event. We don't know exactly when each nucleus is going to decay. Just like I don't know in the 6,437th column how long that particular penny is going to last. There's no way for me to know that. But if we have 10,000 pennies, I can give you a good general sense of how many will have decayed and how many won't have. Just because when we compound that randomness over a really big sample set, those trends come out a lot more cleanly. Okay, I had a lot of fun showing you guys this. Give me a minute and we'll switch back to the more traditional pen and paper format.
Okay, we're back in the regular studio here talking about Half-Life, courtesy of Transparent Physics. And that screencasting was pretty fatiguing, so nice cup of tea to quench the thirst, and then we shall get started. So the idea here is that we are going to follow up with the discussion that I had involving how those pennies decayed, because that's really a metaphor for a larger concept known as half-life. Half-life, again, like the word Spider-Man, should be with the dash in the middle of it. And half-life is the argument of talking about how unstable a radioactive nucleus is. Half-life is, the variable for that is a T with a subscript 1/2. The symbol is not what Valve Games would have you believe, but it is in fact T1/2. Half-life T1/2. The radioactive nucleus occurs, as we talked about in the last episode, when the combinations of protons and neutrons is imbalanced in a way that over time that nucleus is going to randomly fall apart. And even though each individual decay of the nucleus is random, we can actually sort of figure out a pattern in that over time as we get suitably large numbers. And again, the recording that we did on Excel shows us the idea that even though each individual coin flip was random, when we look at it over a large number of samples, we are able to identify a trend. Now, that trend is known as a half-life, and the half-life is the amount of time it takes for half of a sample of a radioactive isotope to decay. So when we were looking at those graphs, we were seeing the decay of half of the sample with every flip. Now, so every one of those flips represented effectively one half-life. Now, the amount of time associated with a half-life varies isotope to isotope, as we'll see. Each isotope of an element has its own half-life, and even isotopes within the same element can vary. Just because they share a number of protons, all carbon atoms have the same number of protons, but if you shuffle around the number of neutrons, those isotopes can have widely varying half-lives in the idea of the amount of time it takes for half the sample to decay. So we can take a look at a couple examples here from across the periodic table, and we can see there's a huge diversity in here. And then again, I could have gone both sides of this, much bigger and much shorter. Carbon-14, kind of a classic one for radiocarbon dating, around 6,000, technically 5,701 years. Lead-210, remember when we're saying lead-210, 210 represents the number of protons and neutrons combined. Carbon-14, that means the nucleus has, when you add the number of protons and neutrons together, you have 14. Lead-210 means that when you add the protons and neutrons together, you have 210. And then different isotopes have different atomic masses. So we go from over 5,700 years to just a little over 22 years for lead-210. Iron-59, a little over 44 days. Mercury-193, about 4 hours. So Mercury-210, about 10 minutes. So Mercury-210, if you had a sample of Mercury-210 at the start of this video, and let's say this video runs about 30 minutes when it's all said and done, you'll start off with 100% of it. Then you'll lose 50% of it, which gets you down to 50%. Then you lose 50% of that remaining, and then 50% of that remaining. We'll talk about that. So you'll have a relatively small amount of Mercury-210 by the time we're done. Just to draw that in, and again, if you notice Mercury-193 and Mercury-210 differ, not in the number of protons, because if they did, they wouldn't be Mercury anymore, but they differ in the number of neutrons. Mercury-193 sticks around for around 3.8 hours for its half-life. Mercury-210, 10 minutes. Very different half-lives. Perhaps more dramatically different, if we take a look between carbon-14 and carbon-15, the mere addition of one neutron to the nucleus radically changes the half-life of carbon-15. Carbon-15 will decay much more quickly. So from the time when this video started, if you had a sample of carbon-15, you probably wouldn't have much of it anymore right now at all. Now the important thing to note is in terms of this phrase, and I'm not much of a musician, but I do have a sense for, I think, good album titles. I think this would be an excellent, I don't know, I feel like this would be a good country album. Half of what is left, not half of what you started with. So I think that sounds like I think I could work with that for a country album. Basically, what I'm trying to emphasize is that when we're talking about half-life, sometimes what people get confused about is they look at half-life in terms of what you initially started with. And half-life doesn't really care about what you started with. When you start half-life, you're looking at the amount that you have right then and there. So if you had 100 grams of the sample to start with, and you come in when there's only 50 grams left, and you look at the half-life from that moment, we don't care that there used to be 100 grams. We are interested in the amount of the sample you had when you start looking at the half-life itself. For each passage of one half-life of time, the sample will lose half of what it had at the start of the half-life. And remember, half-life is a unit of time. Whether it's years or minutes or seconds, Half-life measures the amount of time it takes for half that sample to decay. And the amount that we lose isn't necessarily what we can say just from knowing the half-life. If you have 2 kilograms of a sample of an isotope, or 50 grams of a sample of an isotope, each of those, if it's the same isotope, would lose the same percentage. They would each lose 50% of their initial radioactive isotope in one half-life, but a larger sample obviously is going to lose a lot more. So half-life simply tells us the amount of time it takes for half the sample to decay. But remember, that scales for larger and smaller samples equally. And as an example here, if we take a look at sort of a classic consideration, we have the argument that we start with. Get a little closer. Yeah, you know what? Let's get close. So we have the first sample into focus. You can do it. There it is. All right, so we start with 1,000 nuclei of a certain isotope. Again, whatever isotope it is doesn't really necessarily matter. And what we're going to do is we're going to allow it to have 1 half-life of time pass. How much time is that? Again, it varies by the isotope. If we're talking about lead-210, the passage of time here is 22.2 years. If we're talking about mercury-210, then the passage of time here is 10 minutes. Different isotopes last for different amounts of time. But either way, after one isotope, you lose half of your sample. So we lose 50% of 1,000, and we end up with 500 nuclei. And then we can reset the half-life. Again, we now start with 500 nuclei. These are the ones that are left undecayed. The 500 that decayed, we're not worried about anymore. We're just looking at the original sample. Another half-life passes. Now, some people might say, well, you lose half in the first, and then you lose the other half in the second. That is an incorrect interpretation of half-life. The argument is that you always lose half of the sample that you started with. So we go 1,000 to 500, and then we lose half of 500, which is down to 250. And then we would go from there. Then we'd go to 125, around 63-ish, etc. So the important thing to realize is that every half-life you lose half of your sample. Now, when we take a look at that, we do get sort of a classic curve that we saw in the Excel graph a little bit earlier in the video. The important thing to realize is regardless of what the specific half-life time period is, whether it's 5,700 years or 3.8 hours, when you have a large enough of a sample, they do all follow sort of a classic exponential decay curve. And if we take a look here, this should look familiar to what we saw in the graph just a couple minutes ago. So this sample shows us, if we start with 1,000, after one half-life, we go down to half of the sample that we started with. After 2 half-lives, we go down to half of the sample that we had left over after the first half-life. And then we go half again. So we go 50%, 25%, 12.5%, etc. And we could keep dropping it down further and further and further. A lot of times when I see these graphs drawn in textbooks or online, a lot of times you'll only see this green bar, and I think that's a little bit misrepresentative. It's almost like it sort of disappears into nothing. I like to see graphs drawn with the bar going across here, showing that you still have basically the same mass of your sample, effectively. It's just changing into a different form. And obviously in a real sample, it wouldn't be this uniform. The decayed and the undecayed would be all scattered around each other. This is sort of a simplification of how that decay would actually occur. But the trend line, if we analyze the percentage of isotopes that remain versus the original isotopes, the ones that decay and the ones that don't, we would see this trend followed if we have a large enough of a sample. So we'll wrap up real quickly with a couple things that I find in the process of teaching about half-life, a section that I will call Poetically Things People Screw Up about half-life. And again, a little bit of review of some of the stuff we already talked about, but we'll just run through these ideas anyway. First of all, as a reminder that when a half-life occurs, you lose half of the amount you had at the start of the half-life. It's not how much you had at the start of the initial reaction. Whenever you start taking a look at it, a half-life from that moment, if the sample's large enough, you should have effectively half of the original sample that you had when you started looking at the sample. It doesn't matter that you had 5 kilograms of the sample to start. If you start looking at it when you only have 3 kilograms of the sample, after one half-life, you'll find that you have 1.5 kilograms left. Okay, so that's one point that I think people tend to get a little bit confused about. Second point, and I mentioned that a little bit with the bar graph, when an isotope decays, it doesn't vanish. It often becomes a new element. When we talk about the different types of radioactive decay, we'll see it doesn't necessarily have to become a new element. You can actually undergo a radioactive decay and not change the number of protons and neutrons in the nucleus. But a lot of times when we're looking at it, it will change into a new element, but there's still matter there. So when an isotope, when a sample undergoes radioactive decay, you may not even be able to tell a physical difference by looking at it. But if we do a chemical analysis, we'll see that the ratio of the elements changes over time. But it's still a lump of whatever it is. It's just going to change its nature over time, but it doesn't evaporate or vanish. And then finally, and this is important to note too, is the idea that half-life does not give you insight into the behavior of an individual atom. A radioactive atom will decay randomly. If I have one single isotope, if I knew its half-life, I could give a general sense of whether I think it's going to be around tomorrow or not, but I couldn't tell you for sure, depending on what the half-life was. Now, again, if the half-life's like 3.8 seconds, I wouldn't bet the farm that isotope is still going to be sticking around tomorrow. But if the half-life is 12 hours or 18 hours or 24 hours, maybe it'll be around, maybe it won't. It's hard to tell. Now, if we have more of the same isotope, we will be able to establish trends. We can have a sense of how much will be left. But half-life doesn't give us any insight into individually when a specific atom is going to decay. It simply says when we look at a large enough of a sample, we can tell the trend that's going to occur. We're going to talk about half-life other times as we move through this unit. It is a useful thing to consider when we're talking about isotopes because it gives us a sense of how stable they are. A quick half-life means the isotope is unstable, very unstable, and it will fall apart very quickly. Other isotopes last for longer than human civilization, and they're pretty stable, but they're still not forever stable. And there's a whole range of stuff in between. So I appreciate you spending the time to learn a little bit about half-life with us. Hopefully, courtesy of transparent physics, we've made things a little bit clearer.